Great, here we got another interesting question. So it says which of the following interactions does not contribute to double helix formation? And just look at the questions, try to solve it for yourself. So A, we have base stacking, B, we have salt bridges, C, we have H bonding, D, we have hydrophobic effect, and E, we have favorable interactions between the sugar phosphate backbone and water. All right, I assume you have looked through it already. So let's start with option A, which says base stacking. Base stacking definitely does contribute to double helix formation. In fact, it's actually the most important stabilizing force in the double helix. The flat aromatic ring of the nitrogenous bases stack vertically on top of one another, and that is stabilized by van der Waals forces and pi-pi interactions. Okay, so I'm going to put that down. This one is most important and involves van der Waals forces and there's also pi-pi interactions. Okay. And B, we have salt bridges. And what do we think? Salt bridges? What are salt bridges? Well, you probably already heard of it, but salt bridges are just a specific type of non-covalent interactions. So they're non-covalent. So first, we already know it's not A, so we can eliminate that. Non-covalent, and it combines electrostatic, that's very important, the electrostatic attraction, so that's ionic interaction. And there, it's also mixed with hydrogen bondings. But yeah, it typically occurs between positively and negatively charged amino acid side chains in proteins. Okay? And it is non-covalent. So usually between positive and negative side chains in proteins. And does it happen in helix formation though? Well, think about it. What is the primary charge of sugar phosphate backbones? Well, sugar phosphate backbone, they contains highly negative phosphate group, PO4 3-, right? So, and those, they're all negatively charged, and because they all carry the same negative charge, they actually repel each other. So, would they form stabilizing salt bridges with each other? No. These negative charges act, in fact, they must be shielded by surrounding water molecules and positive metal ions like magnesium or sodium in the cellular environment to prevent the double helix from flying apart. So it's actually, salt bridges is actually a disrupted force. So it is the answer here. So it's actually it's a repelling force, okay, because you have this repelling force between those PO3, PO4. So PO4 2 3-, right? So it's a repelling force, so it definitely doesn't contribute to double helix formation. So how about H bondings? Well, we know hydrogen bonds form horizontally between complementary base pairs. So A pairs with T or G, A pairs with T, and G paired with C, right? So that's the common base pairing conventions, and they are actually based on hydrogen bonding. So we have A with T and G with C. And yes, those does contribute to stability, but the primary job is providing this specificity that ensures the strands match up correctly. So it is. Let me put it down here. Stability. That's one part, but it's actually not the major part. Plus specificity. That's the major part. Specificity. Very important. Okay. And then option D, hydrophobic effect. The nitrogen bases, they're relatively hydrophobic, right? But the sugar phosphate backbone is actually highly hydrophilic. And to minimize free energy, the hydrophobic bases hide inside the core of the helix away from water, driving the structure to twist into a double helix. So this one is also very important, right? Because of the hydrophobic effect, we have the bases being the middle in the inner part of the double helix, and we have the phosphates sugar being outside of the double helix. And it does a very important role of twisting the entire structure into a double helix. And then finally, it says favorable interactions between the sugar phosphate backbone and water. Sugar phosphate backbone and water, while the negatively charges on the sugar phosphate backbone form highly favorable hydrogen bonds and dipole interactions, right? So there's, they actually does form H bonds, dipole interactions. So, and that's 100% true, right? They form it with the surrounding aqueous water environment, keeping the outer shell of the DNA soluble and stable. So that's also very important. So we can omit that. And the final answer is that salt bridges does not contribute to double helix formation.